Hi, I'm Riad, and I'm going to talk about, this is a little bit of a gear shift. This is talking about airdrops. It's related in the sense that we're kind of using some of the same underlying structure. So we all kind of have this idea in our heads that starting a new cryptocurrency is hard, and yeah, there's a lot of code to write and stuff like that, but that's like kind of the stuff we're good at. The stuff we're bad at is like getting people to like us. Or, okay, that's me. But so like the way that you actually do that in practice is it turns out you just give people money. And so like this is what people do. So like, for example, Stellar has done a couple of these big airdrops. They had one a couple years ago. They had one like last year with Keybase. And so what was going on there was that they said, look, we want to be able to somehow like give people money without requiring them to interact with us first. So they don't have to ask for money. Well, maybe in the Stellar case that wasn't quite true, but like in the ideal case, like you don't really have to ask for money. You just like, you get it, and then like you can spend it if you want to, which is cool. So the question is, how do you do that? And like this article kind of gives us a hint. They're dropping to Bitcoin holders. So what they're doing is they're basically using Bitcoin as a PKI, right? They're getting the Bitcoin addresses and then just sending money there. But Bitcoin isn't the only PKI you could imagine using. Like you could imagine using like GitHub or something, or like you know, web certificates or something like this. And that's awesome because like there are, I don't know, 100 million like web certificates or something according to Let's Encrypt. And so that's super cool. But now there's a problem because if I'm like one of these people and I want to claim my funds, then I'm sort of indelibly like saying like to the world, I'm willing to take funds from this person, and maybe this person is like sketchy person, and I don't want to admit that I'm willing to take from them. And in fact, if we talk about the GitHub case, then it's even worse because maybe like I work for somebody who like requires me to do stuff on GitHub, and so now like my employer gets nervous because I'm like using an identity that's linkable to them to like take money. So okay, so this is the problem, and in fact. It turns out, like we were talking to some folks at Handshake about this, and they said, actually, we're pretty worried that this will actually cause people to not want to claim funds from us. And we don't want that. So what we want is to be able to give people funds without letting them, without revealing that they've actually claimed the funds, because we want to avoid this disincentive for privacy conscious recipients. Okay, so that's the goal. And so how are we going to do that? Here's a bad idea. The bad idea is like I'm the person now sending money to you, and what I'm going to do is I'm going to generate a private key, and I'm going to just email you the private key, maybe encrypt it under your existing key, and that kind of works, except that now anyone who watches the airdrop happen is like, well, yeah, but I mean, did he really send anyone money, or was it just like, is it just like sort of a shell game? We don't want that. We want to be sure that the only person who can claim the money is actually the person that we intended to airdrop to, okay? Yeah, basically we don't want to have to trust the sender. Okay, so here's a slightly better idea. The better idea is the recipient is going to produce a zero-knowledge proof that they know a key, or that they know the secret corresponding to some public key, and that they haven't previously claimed the airdrop, but they're not going to reveal which key they're talking about, just that it's one of the ones that's in the allowed set. So we tried to do this by like just using a general purpose proof system. There are many of them out there. And what we kind of quickly realized was, well, yeah, it works, but it's like for one reason or other, it's not so great. So maybe it's too slow to generate the proofs, or maybe we need some kind of trusted setup. And if the trusted setup is done wrong, then the sender could just like make false proofs. So again, we kind of have to trust the sender. And so somehow like these general purpose zero knowledge proofs didn't quite get where we wanted. So the high level goal of this work was, can we somehow have a special purpose zero knowledge proof that's tailored to private airdrops and that's inexpensive and maybe doesn't require trusted setup? Okay, and so that's what we do. We define what we call private airdrop schemes, and you can think about these as kind of a special kind of signature. And we show basically how to construct private airdrops from ECDSA and RSA keys. And here I'm going to basically ignore ECDSA, or I mean EDDSA also works, but that construction is pretty straightforward. The more interesting case is the RSA case, and there we kind of need a new zero knowledge proof of knowledge of factorization of a hidden integer. So that's like the underlying thing, and this is actually using some of the same machinery that a lot of the VDFs do. We also, in the paper, we describe what we call a private genesis airdrop, which is a way of sort of extending the private airdrop to like millions of users, each having like 1,000 keys or something like this. And the idea is, well, this should be practical to actually privately airdrop to like 1 million people all at once. And finally, we implement and we evaluate, and the high level point is that for RSA, which is the expensive case, generating a signature takes like tens or maybe hundreds of milliseconds, and verifying takes single-digit milliseconds, and the signatures are around 2 or 3 kilobytes. So pretty practical. I kind of mentioned the elliptic curve case already is not so interesting. It's basically exactly the same cost-wise as generating a signature under like EDDSA or ECDSA. Okay, so in the rest of the talk, very quickly, I'm going to give you some like high-level ideas of like what a private airdrop kind of looks like in practice, and then I'll talk a tiny bit about the scheme for RSA keys. So another way that we can think about the requirement for the private airdrop is we want to create an unlinkable identity from an existing public key. So in particular, let's assume that the recipient has some public key and knows the corresponding secret. And then, so here's how the private airdrop is going to work. First, we're going to have a sender who's going to create what we call a token and a corresponding secret for that token. And then they're going to publish the token, and they're going to encrypt the secret and send it to the recipient. That's it. That's the setup. That's how you like send somebody an airdrop. And then if I want to claim the airdrop, I need to know the token and the secret corresponding to the token, and I need to know my secret key that corresponds to like the underlying key. And then I can generate a signature using the private airdrop scheme on the message. And then anyone can verify the signature without learning anything at all about the underlying key. Right, so all they need to know is the token. They don't learn anything else except that this token got claimed. Done. Okay. So this is, so we need kind of 3 properties for security. I'm going to give a very high level notion of each one. So first we need anonymity, which is just what I said. You don't learn anything by seeing a signature or the token. Like it's just, okay, somebody claimed and there's no way to link that to the underlying key. Second, we need unforgeability, which is basically the same notion that we have in signatures. It's hard to create a false proof or a false signature. And third, we have what we call orthogonality. And this is something slightly different. So if we're deriving one key from another key, we have to make sure that a signature under the derived key doesn't somehow break the underlying key, right? Because otherwise I should have no reason to produce a signature. I would, like, if you can't convince me that I should break my key, or at least I hope you can, right? Okay, good. This is kind of related. I just want to point out to a few other sort of existing notions. So group signatures, I guess, is what we're kind of most closely related to. In the group signature setting, we have somebody who sets up like a group, and then anyone in the group can sign, and all we learn is that somebody in the group signed. So here, it's basically a group signature where the group who can sign is one person, and the people who could be in the group, like the anonymity set, is essentially anyone who owns a key of that type. So it's like an asymmetric group signature. There are also ring signatures, which have a sort of similar flavor of some anonymity set, but actually these are not exactly what we need because the anonymity set is ad hoc and is determined at the signing time, so it's not too close. And then I should also point out there are these CryptoNote stealth addresses. This is actually, they get some nice properties that are very comparable to private airdrops, but the main drawback in our setting is that the CryptoNote stealth addresses actually need a special public key format in order to work, whereas we need to be backwards compatible with existing keys, because the whole point was we wanted to be able to like airdrop to people on GitHub or something like this. Okay, so now very, very quickly, the high-level ideas of how the scheme for RSA works. So as we know, an RSA key is basically, we have a modulus that's a semi-prime, and the secret is essentially the factorization of the modulus. And so the first idea is to prove that I know my secret, I just have to prove that I can factor the public key. Okay, makes sense. So how do I prove that? Well, one way I could do that is I could show that I can take square roots mod n, because it turns out that if I can take square roots, arbitrary square roots mod n, then I can also factor n. And the third idea, remember, we need to be able to actually hide what n is. So now we hide n inside of a Peterson commitment. Okay, so now we have sort of all the pieces that we need in order to put together a zero knowledge proof for, it's sort of a mess, but we can read through it. Basically, the public statement is the commitment to my key and some small prime, like a prime under 128 or something like this. And then the proof is that I know how to compute a square root mod whatever's hidden inside of the commitment of that small prime. Okay, so I've proven to you that I know how to compute square roots mod my modulus without telling you what my modulus is. And I should note that this actually does reveal one bit about n, because for any given t, you can check that t couldn't possibly be a square mod n for half the n's in the world. So I'm really only telling you something. I'm telling you that, yeah, the modulus can't be on that side of the room. It can only be on this side of the room, this sort of thing. But you might want to avoid that. So actually in the paper, we also talk about another way to do this, like maybe even more straightforward. To prove that I know how to factor n, I can give you a commitment to n, and then I can give you a commitment to its two factors, and then I can prove that indeed they multiply to the right value, and that they're non-trivial, right? They can't be plus minus 1 or plus minus n, because, well, anyone can do that. So this doesn't leak a bit, which is nice, but the downside is that the proof is a little bit longer, maybe 20 to 80% longer, and more importantly, verification is about 5 times more expensive. So maybe you don't want to leak a bit, totally fine. This protocol works. Otherwise, the other protocol gives you slightly better verification time. And finally, there's this question that I kind of glossed over, which is, okay, but we need a commitment to an integer, my modulus. How are we doing that? We're going to be working in a group of unknown order. And so one way to do that would be an RSA modulus of unknown factorization, unknown to everyone. And so this means either a trusted setup or maybe some sort of MPC, very much like the one that is happening this afternoon. You should go and participate. And the other option is what we heard in the last talk. You can use a class group to do this as well. The upside is that there's no trusted setup. You just choose a random prime. The downside is it's a bit slower. It looks like maybe 10x slower overall, but maybe things are getting better. So maybe it's only 3x slower nowadays. Maybe I'm not totally up to speed, but it seems like there is a little bit of extra cost there in terms of the computation time. Okay, so I'm going to wrap up real quick. So our private airdrops work for Diffie-Hellmanish keys and for RSA keys. And basically the RSA one is where all the magic is happening, and this is with a new zero-knowledge proof of factorization. And we also talk about how you can airdrop to millions of users. So the RSA one is a bit more expensive than just sort of privacy-free RSA signatures. You know, maybe 10x more expensive to sign, and maybe 10x more expensive to verify. I don't know, maybe 100x more expensive to verify. But in absolute terms, that's okay. We're talking about like single-digit milliseconds to verify. So this is something that one could reasonably do. And this is actually deployed right now in the Handshake airdrop, which is ongoing. So you too could run one of these RSA signatures. And with that, I'm happy to take any questions. No. Thanks. Yeah.
Could you give any intuition for how you do the, so in the case where you're proving knowledge of a divisor of the modulus, how do you show that the divisor you're demonstrating isn't 1 or plus or minus n, et cetera?
Sure, good question. So there are a few ways to do this. What we do is a little bit weird, but so here's one way. If I want to prove to you that something isn't equal to is not equal to 1, then like let's say you have a Peterson commitment to my thing, which is p. You can easily compute a Peterson commitment to p minus 1 from that, and then I just have to prove to you that that commitment is not 0. Right, so how do I do that? Well, if I can give you another commitment that commits to the multiplicative inverse mod some prime, and then prove to you that like that exists, that it's actually like the product is actually 1 mod some prime, then that's enough. So I can basically it's sort of a few little tricks to get something that looks like this thing is not equal to 0. Does that
totally
kind of work?
Thanks.
Thank you.
Okay, thanks.